This lab is Lab 9 Diffraction, presented by me, Jahaziel Galvan, and
Luke Thoresen.
Sweet. This is the overview of the lab. We're going over Part A, which is diffractive apertures, and Part B, which is measuring laser beam divergence. We'll be going on Part A, which is diffractive apertures. Our source is a red LED laser, and our objective is to observe and compare different diffraction patterns from various apertures. And down below is our listed equipment, and here's a photo of our setup. If you look here and pause whenever you want to look at it, is a procedure in which we did to collect our measurements. All right, so what happened is that we had many different apertures, such as double slit, single slit, triangle, rectangle, square, circle, etc., etc. And we use ND filters to get these results as you look on the right side. What happened is that as we moved from our differential position to our, sorry, I forgot, APP position, there was a change or more so a shift, and you can be seen in our results that will be shown right now. As you can see here, as we move from dip position to aperture position, you can see that there was a shift more as an elongation or stretching in the X and Y, or more so rotation. You can see the stretch happening from the rectangle and in the square. However, you can see the rotation or the inversion with the circle and the triangle. And for the single slit and double slit. So for the single slit, what we did is that we got position A and position C. And in between there, we got three different positions, position B1, 2, and 3. And if you notice, as we move from position A to position C, the diffraction pattern started shifting from long to more so vertical. As for a double slit, it completely went from being horizontal to vertical.
So for part B, we measured the laser beam divergence as well as the beam waist and the numerical aperture of a helium neon laser. And this was done using a commercial beam profiler. So beam waist is a crucial concept when working with lasers. It is determined by the waist size, and it goes kind of diverges, converges, and then diverges again. And that beam waist diameter equation, as well as the Rayleigh range and numerical equations or numerical aperture equations, are shown in the top right. And we used the commercial beam profiler and software data array to quantify the beam waist at multiple distances. So here are our results. You can see the near field and far field graphs on the right, the distance versus beam profile, and our values for the waist distance was about 10 centimeters, and the minimum beam waist diameter was 567 microns. And that gave us a Rayleigh range of about 1.6 meters, a divergence angle of 1.28 arc seconds, and a numerical aperture that is very small. And this makes sense because it's a laser and it's kind of narrow beam of light. So it would make sense that it has a low divergence angle. Thank you.
Thank you.